We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India.
Dear students, welcome to today's class. The topic of today's lecture is one-way continuous slab. As the name shows that this type of slab is different from a simple one-way slab, rather it is a one-way continuous slab. To understand this type of slab, it is better to go through its support system. The slab is continuous, that is extending from one span to another span and then to another span. The number of supports always has to be more than 2. In this case we have taken 4 supports, that is to have a one-way slab comprising of 3 spans. The span length is here taken 3.2 meter and the length of the slab is Ly. This can be any value according to the situation of the building. So if you see that the space between 2 supports is for one-way slab, that is one-way slab, and for this one-way slab the ratio of Ly upon Lx has to be more than 2. Similarly, the second space between these 2 supports is again a one-way slab, and the third slab is also a space is also going to become a one-way slab. So all these 3 spans are connected with their slabs, and this type of connection is possible by means of constructing a one-way continuous slab. Continuous because the concrete material and the reinforcement of this span is extending to another span and to the further next span, and this type of monolithic construction, that is the construction of all the 3 spans slab at the same time with the same type of material. So homogeneous material and the same time construction is going to make the slab hard at the same time. So this all 3 span will be comprising of a one-way continuous slab, which is going to have a different characteristic than a one-way slab. So as far as the support are concerned, I think you might have learned that there are the several supports in one-way continuous slab. So this supports has to be covered by a big slab. So and this is a one-way continuous slab because this slab is going to provide the rooftop to the supports. And if we visualize the supports on the surface of the slab from top, then you can see that the dashed line shows the position of the supports below the slab. Now between 2 supports we have the one-way slab portion, and this slab area, the second span area and third span slab area are each to be designed by a collaborative method as per guidelines of IS 456-2000. Now the most important aspect of a one-way continuous slab is its deflection pattern, that the one-way continuous slab is going to deflect once it is fully loaded from top, and under the action of the load the slab is going to have some bending moment in each span. Under the influence of that bending moment, the slab is going to bend. This type of sagging bending in each span would occur, but the nature of bending on the support area is different. When the span bends like this in the span area, is going to bend in opposite nature over the supports. So if this is a sagging bending, this is called as hogging bending. In this sagging bending area, what is happening, that the tensile stresses are developed at the bottom of the slab, and the tensile stresses in the hogging bending area, that is above on the top of the support, is going to develop on the top of the slab. So this type of bending of each span is going to exhibit that where is the need of reinforcement at which portion. In the span area, in the mid span area, it is required at the bottom of the slab, and near support area it is required on the top of the slab. So entirely the whole span throughout its length Ly is going to have the similar type of bending. And if we see this, if having a imaginary slab in this case, then it would look like a slab covering with folded surfaces. You can see this span is having a downward folding, near the supports it is having a upward folding. So the flat slab which was initially in the first image is going to have a deflected pattern, and this becomes like this. So the one-way continuous slab is going to deflect continuously, and each span is affected under the influence of the load and its bending moment. Now, to better design and understand the procedure of one-way continuous slab design, there are several design steps, starting from the calculation of effective depth, then the load calculation separately for dead load and live load, then the load calculation for effective span, the calculation for bending moment, then the check for depth in flexure, calculation for main steel, calculation for distribution steel, check for cracking, and finally the reinforcement sketch. So one by one we will take up the procedures. For this we have taken a design problem of a continuous slab having 3 equal span, each of 3.2 meter, with following data. The imposed live load is 4.5 kN per square meter. The floor finish is 1 kN per square meter. We have to use M20 concrete and Fe415 steel. With this data, the first step is the effective depth calculation. So as per IS 456-2000, page 3738, figure 4, from deflection control criteria, assuming a steel percentage of 0.6% for Fe415 for a continuous slab, from figure 4 we get L/D ratio 26 multiplied by modification factor, and when you see the 26 multiplied by modification factor we get for this percentage, and this is steel 1.15 from figure 4, so this becomes 29.9. Now D comes the Lx by 29.9, that is 3200 millimeter by 29.9, that is 107 millimeter. So with this small d value we have to calculate the total depth, that is overall depth of the slab, capital D, that is small d, plus the bar diameter assumed by 2, plus the main clear cover below the main steel bar at the bottom of the slab, 20 plus 20, that is 107, plus 5 plus 20 becomes 132. So we have overall depth, that is 132 millimeter, and the effective depth, that is 107 millimeter. With this, the next step is to have a load calculation. So here we have to calculate the dead load and live load separately. As given in this problem, the dead load is capital D, that is 0.132 millimeter, 132 millimeter, so that is 0.132 meter, multiplied by the design width of the slab. We generally take 1 meter wide slab for design, multiplied by 25, the density of RCC, equal to 3.30 kilonewton per meter. Now floor finish given 1, this is the 1 into 1, that is 1.0 kilonewton per meter. The total dead load adding these two becomes 4.3. Now factor dead load 4.3 multiplied by the partial safety factor for load becomes 6.45 kilonewton per meter. So this is the total dead load per meter run, and then the live load given 4.5 into 1, that is 4.50 kilonewton per meter, and then factored live load, so 4.5 is multiplied with 1.5, partial safety factor for load is 6.75 kilonewton per meter. So we have now the total dead load, UDL, uniformly distributed load per meter run, is W dead load 6.45 kilonewton per meter, and W live load 6.75 kilonewton per meter. So with these two loads we have to now calculate the bending moment, but before that we have to calculate the effective span. So as per IS 456-2000, page 34, clause 22.2b, important condition in case of continuous slab is that we have to take the shortest clear span divided by 12, that is 3200 by 12, that is 266.66, and this is more than the width of the wall, 300 millimeters generally we take. That is, in this case, with this condition, the effective span L becomes equal to clear span Lx, that is 3200 millimeter. So effective span L is here 3200 millimeter for next step. So this step, that is the calculation bending moment, is quite important in kilonewton meter as per IS 456/2000, page 36, table 12. If we draw a sketch like this, that is of a continuous beam, a continuous slab with 1 meter width is similar to a continuous beam. So it is having supports A, B, C, D, and the midpoint of each span E here, F here, and G here. So that is end span, intermediate span, and again end span. So for this, a UDL load applied throughout the span. The load is 6.45 kg per meter for dead load, and live load 6.7 kg per meter. So with this, and referring to table 12 in IS 456, we get some bending moment coefficients. So for point A and D, the bending moment coefficients are 0 because they are simple supports, so there the bending moment would be 0. For point E and G, that is the midpoint of the end span, the coefficient is +1/12. And for B and C, that is the support, top of the support, the bending moment will be there, negative bending moment will be there at B and C. So for this, the coefficient is -1/10. And for the mid span of the intermediate span, midpoint of the intermediate span, the coefficient is +1/16. This is for dead load. Again for live load, these coefficients are there for the respective points, +1/10, -1/9, and +1/12. Now we have to calculate the bending moment. So bending moment for dead load coefficients is +1/12 multiplied by the UDL 6.45 multiplied by the span. So that is multiplying all these three, 1.72 kilonewton meter. Similarly for BC, it is -1/10 multiplied by UDL, that is 6.45 multiplied by span, -2.06, and similarly here, that is 1.29 for the point F for dead load bending moment by using the dead loads. Now the bending moment using the live load, for this is +1/10 multiplied by the UDL 6.75 multiplied by span, so this is 2.16, and for this BC it is -2.40, that is -1/9 multiplied by UDL 6.75 multiplied by span 3.2, and then this, that is 1.8. So by taking the sum of all these two moments, bending moment because of dead load, bending moment because of live load, the total comes 3.09. Here the total of these two is -4.46, and the total of these two is 3.88. Now we have for all critical points the total value of bending moments. So out of these three values, the highest value in magnitude is 4.46. So corresponding to this value, we will now calculate the effective depth in flexure criteria. So as per SP 16, page 10, table C, the given formula is mu lim 0.13 FCK BD square. From this, mu lim is equal to the maximum value of moment there, that is 4.46 into 10 to the 6 divided by 0.138 and 20 multiplied by 1,000. This gives d, small d, 40.19. Taking the square root of all this is 40.19. So this depth is less than the adopted value of the depth in the load calculation, that is 107 millimeter. So it's okay. Now the next step is calculation of main steel AST value. So this is done as per IS. This is done as per SP 16 table 2 for M20 concrete. Required ratio is mu by BD square. As we have this, we have done in the case of one-way slab also. So at point EG, EG means the midpoint of the end span. Midpoint of the end span. You can see here the midpoint of the end span E and in midpoint of the end span G. So at the midpoint of the end span, we get mu of VD square, the total moment 3.18 into 6 divided by 1000 and 107 square, that is d square. So this is 0.3388. For this ratio from table 2, we get PT 0.0958%, and using this percentage, the AST area of steel comes this percentage into the B value into the D value divided by 100, that is 102.5 millimeter square. Now you see this area, that is percentage very less. The minimum percentage is still required in any direction in slab. For Fe415 steel grade is 0.12%. So this minimum steel required is 158 millimeter square. Now the calculated value is 102.5, so we have to provide the minimum area of steel as per the IS code. So if we assume 8 mm diameter bars as main steel, the spacing between the bars would be this into 318 mm per center to center, but as per IS code this cannot be more than 300 mm, so we would provide 8 mm dia bar at 300 mm center to center as main steel for the point E and G. Now for the point F, that is the midpoint of the intermediate span, so the total moment for the midpoint F is, you can see in the diagram, for F this is 3.88. so for this moment we have to find out MUAVD square, 3.88 times 6 divided by 1000 divided by 107 square, the D square, so this comes 0.3388. So the percentage of value PT comes 0.0958%. So corresponding to this percentage, the area of steel AST comes by putting all values 102.5 millimeters. Again, this is less than the required percentage. So required percentage, and this way the steel area for minimum steel area required is 158 millimeters square, corresponding to 0.12%. So if we assume 8 mm diameter bars as main steel, spacing of the bars again comes 318 millimeters center to center, and this is the maximum allowable value is 300 mm. So we would provide 8 mm diameter bars at 300 mm center to center for the points E and G. This we have done. Now again we have done for the point F. So MUAVD square ratio comes 3.09. so you have seen the diagram, 3.09 for F value. So 3.09, correspondingly putting all values we get 0.2698. so the PT comes 0.085%, and corresponding to this percentage the AST comes 90.95 millimeters square. Again this is less than the minimum percentage 0.012 and the area 158 millimeters square. So we provide again the same minimum steel area, that is 8 mm diameter bar at 300 mm center to center for the point F, that is the midpoint of the intermediate span. Now the third point is the top of supports, that is B and C. So for there the value of moment we already calculated, this is 4.46. so for this moment we have calculated putting all the values, BD square, this is 0.3895, and corresponding to this ratio the percentage of steel PT comes 0.1108. so corresponding to this percentage the AST area of steel comes multiplied in BD by 100, this is 118.5 millimeters square. Now this is again less than the minimum steel required 0.12%, this is only 0.11%. so we again provide the minimum steel required, that is 8 mm diameter bars at 300 millimeters center to center. So this way we have calculated all main steel areas for the all critical points in the continuous slab. Now the next steel required is calculation of distribution steel area. So as per IS 456/2000 page 48 clause 26.5.2.1 for FE 415 steel type, the area of distribution steel is again 0.12% of B times capital D. So this comes 158 millimeters square. So if assumed 8 mm diameter bars, spacing between bars is 50.26, that is 1 dia bar area multiplied by 1000 by 158.4, this comes 317 millimeters center to center. So for distribution bar we would provide 8 mm diameter bar at the spacing of 317 millimeters center to center. So this is our distribution steel area and its spacing. Now check for cracking is important to check the spacing what we have calculated. According to IS 456/2000 page 46 clause 26.3.3b, the maximum spacing should be 3D, 3 times D 321, then 300 millimeter, and again we have calculated here it should be 300 for all points. So the 300 millimeter spacing is recommended for all the points, but for distribution steel it should be maximum 5 times D, then 535 millimeter or 450 millimeter or calculated 317 millimeter. So a smallest of these 317 millimeters, so we will provide 8 mm dia bar at the rate of 317 mm center to center for distribution steel. Now the most important part of this design is the reinforcement sketch. If you can see, the reinforcement sketch is for the top portion, that is the plan. In plan you can see the top, the one bar, that is you can see the red bar is coming from the right support in this span going to the next support, and a distance of, this is continuous support, so this is L by 4 and the total span L by 4. Then from that point it is bent up and goes to the top of the support coming from the right side. So in each span the one bar is coming from the right side and going to the top of the support, the next support, and this way you can see. But for the next bar, alternate bars are coming starting from different ends. Here the black bar is coming from this support going to the next support, and here since this is a discontinuous end support, so taking L by 7 from this support, and then from that area point it is going bent up and extended to the top of the support. Similarly in this span also the next bar is coming like this and extending to the next support. So the next bar will start from this end and going to the top of this support in this everywhere. So everywhere alternate bars are bent up on the support. If you see this support, this one bar is bent up here, another bar is at the bottom of the support, next bar is coming on the top of the support. So at every point you can see on the support alternate bars are bent up and alternate bars are at the lower portion of the slab. So in each span the reinforcement and the placement of the bars are ensured like this. You can see here in the mid span area all bars are there. So this is 8 mm diameter bar at 300 center to center. In this span also the bars in the mid span area is 8 mm diameter at 300 center to center. But when the 50% of this area goes near to the top of the supports, then between black bars the spacing becomes double of 300 or 600. Between red bars the spacing becomes, these two red bars, double of 300, that is 600. But including all, the spacing between one black and one red on the top of the supports will be 300 only. So between two bars the spacing is maintained 300 mm center to center on the top of the support as well as in the mid span area. Same trend is maintained in each span. So the blue bars which you see here are the distribution bars, that is 800 mm bars, dia bars at 317 mm center to center, that is all blue bars, that is on the top of the main steel bars, in the bottom of the slab as well as in the top of the slab. So the purpose of the distribution bar here is to keep the main bars at exact position which is meant for them and get tied up with the main bars and proper protection of the slab against temperature stressage and shrinkage stressage. So if this whole slab is taken a cross section along x-axis, then it will be visible like this. The red bars here starting from this support going near this support and bent up from a distance of L by 4. In this span the one bar is coming from this area from the bottom and going to the L by 7 length of the support and then bent up. Similarly in this span the red bar is coming going to the next support and the black bar is coming from the bottom and going to the top of this support. Similarly at this end span also. So this trend is maintained throughout the whole length of the slab. Now the white circles are the distribution bars which is shown here in the blue line. The blue line distribution steel is shown here, the white circles, which is provided on the top of the main bars and below the upper bars. The top of the lower bars, lower main steel, and below the upper main steel. So the main steels are the main responsible bars to take the tensile stresses, and the distribution steel bars are responsible to keep the main bars in the proper position and protect the slab against all temperature and shrinkage stresses during the concreting and hardening processes of the RCC. So again the same diameter of bars has been shown here. This is the bottom bars, 8 mm dia, 300 mm center to center, and again here the same dia, same spacing, and the distribution bars are 8 mm dia, 317 mm center to center as shown, and this is the same steel bars everywhere. So by this way we have shown the plan of the reinforcement sketch as well as one XX long cross section, which is where the depth of the slab is visible, and along the depth the reinforcement position is also being shown. Now if we see a three-dimensional view of the reinforcement placed in this continuous slab, how it looks, you can see here that in this diagram the slab, the whole depth of the slab is having the same type of reinforcement as seen in the cross section before, and whatever is the bars placed on the top in the cross section is visible on the whole length of the slab in the top area you can see here. Now these bars are on the top, so below the bottom bars here and the top bars is some vertical gap is there. To maintain this vertical gap, some chairs are provided between the two bars, so that when the casting is carried out these bars are not getting disturbed, and this gap between the lower bar and upper bars are maintained, because the position of the reinforcement bar is more important than its number or anything in the RCC. So with this hope that you have understood the main points of one-way continuous slab, its reinforcement detail, its design steps, and what are the main risk of a continuous slab is its deflected shape. If the deflection is excessive, the slab may collapse, slab may crack, slab may break. So by perceiving the deflection risk, wherever the need of tensile reinforcement is required, to design the reinforcement and place at those specific critical position, critical locations, will protect the slab against all types of stressage, that is tensile stressage, temperature and shrinkage stressage. So with this hope you have understood the one-way continuous slab and its design steps. Thank you very much for patiently listening the lecture. Thank you.